Okay, so we're going to be looking at AQA AS Physics 2016 paper 1. And as per usual, sorry that I can't show the paper on here because otherwise AQA will get my channel deleted, much like they nearly did in the past. Okay, question 1, we have this jet engine. And question 1.1 implies that it's all going to be about momentum. So, what is happening to the momentum of the air as it goes through the engine? We know, of course, nice and easy, the momentum increases. 1.2, how does that result in a force on the engine? What laws of motion can we employ? We can always employ the third law, and it's either the first or second law in either situation. The third is always true, and it's either first or second, but because we have acceleration, we are going to be doing the second law too. So let's deal with our second law first. Newton's second law, force is equal to mass times acceleration, or force is equal to rate of change of momentum. So we can say, as air is accelerating, engine exerts force on it. We can say that's the second law. However, Newton's third law states that to each action must be equal and opposite reaction. Therefore, air also exerts force on engine in the opposite direction. Time for some calculations. We're told that in 1 second, so therefore we have a time of 1 second, mass of 210 kilograms, and the speed increases. So we can say delta V is equal to 570 meters per second. We're being asked to find the force. We just wrote down the alternative version of Newton's second law. That is, force is a rate of change of momentum. It can be the mass or the velocity that's changing. In this case, it's the velocity, so we can say that's just the same as the mass times the change in velocity divided by the time taken. So that's just going to be 210 times our change in velocity, 570 meters per second, divided by the time of 1 second. And that is 119,700 newtons. Our data was given to a maximum of 2 sig figs here. Therefore, we can give our answer to 2 sig figs there. I always wondered this when I went on planes growing up. How was it that the jet engines provided a force going in the opposite direction when you land? It wasn't like the turbine starts spinning the other way. It can't do that fast enough. No, you have these deflector plates that shunk in behind the jet engine, and then the air is deflected forward. So explain why the momentum of the air changes. So the first thing we know is that if change in momentum, there must be a force. Therefore, deflector plates exert force on air in left direction. But we're told that the speed is the same. So we can say, even though speed is same, direction has changed, therefore so has velocity and momentum, like we said above. Not a well-worded question because they're actually only looking for this point here. But if they ask you something like this, it's always best to put down as much as you know about what is going on in this particular situation. We're told that the decelerating force is 190 kilonewtons. Let's put that in standard form, 1.9 times 10 to the 5 newtons. And we have a mass of 7 times 10 to the 4 kilograms. And we're being asked to find acceleration. So therefore, easy peasy, we're just going to use F equals ma. But we need to rearrange, so acceleration is equal to force divided by mass. So that's 1.9 times 10 to the 5 divided by 7 times 10 to the 4. And neat little shortcut, we can get rid of some powers of 10. So we have times 10 to the 5 on top, times 10 to the 4 on the bottom. So we can take 4 away from that 5 on top. So that ends up being just 1.9 times 10 to the 1, or in other words, just 1.9 times 10 on top. So that's 19 divided by 7. And that is, well, to 2 sig figs, because that's what our data was given to again. That is 2.7 meters per second squared. Next, we're being asked to find the distance that the aircraft travels as it lands. Now, we're being asked to find a distance. We're either going to use just speed equals distance over time or suvat. What's the difference? It's when there's acceleration or deceleration. When there's an acceleration or a change in speed, we have to use suvat. If there's a constant speed, then we just use speed equals distance over time. So let's write down our variables. We're looking for s. We're told that the initial speed is 68 meters per second. Do we know v, final velocity? Yes, we do, because we know is coming to a standstill, so it's 0. And we know the deceleration from earlier is 2.7 meters per second squared. And we're not concerned with the time. Now, you don't need to turn the acceleration into a negative number just because it's deceleration. The only time that it's worth turning numbers into negative numbers is when you have things going in opposite directions. If you have an object that is thrown up and comes back down. Okay, now technically, if u is positive, then a should be technically minus 2.7 meters per second squared. But it doesn't matter because we are going to end up with the same answer in the end. So which equation are we going to use? The one without t in, so that's v squared equals u squared plus 2as. V squared is 0, so therefore we can say that u squared is equal to minus 2as. And that's where the minus takes care of itself. So actually, if we just ignore that, we still end up with the same answer. If you're unsure about that, then sure, do it properly, but this just a little shortcut for you there. We're looking for distance, therefore s is going to be equal to u squared divided by 2 lots of the acceleration. So that is 68 squared divided by 2 times 2.7. And I end up with a number of 856 point something. But again, we've been given our data to 2 sig figs, so we're just going to round that to 860 meters. And finally, 1.7. Why isn't the force going to remain constant? Well, in order for the force to remain constant, the air needs to be going the same speed into it. So we can say as plane slows or as plane decelerates, change in velocity of air decreases, therefore so does decelerating force. And we could also add in here and change in momentum. Okay, question 2, all about stationary waves. 2.1, how is the stationary wave formed? This is a question that you must know the answer to. It always comes up, and it goes for whether it's EM waves or a wave on a string or other waves as well. So we can say that the emitted wave reflects off the oven wall. Reflected wave interferes or superposes with incident wave. That's the one just going into the oven wall. Now, here's a point of contention. AQA love moving the goalposts. So back in the day, you used to be able to say superimposes years ago. Superimposes was fine. They don't like that now. It has to be superposes. But this mark scheme says interferes is fine as well. I like interferes because that makes sense. When waves interfere, they make a stationary wave, or they can make a stationary wave. However, lately, AQA have even said that interferes is not okay. I think that's absolutely ridiculous, but for some reason AQA have an absolute obsession with this word superposes. That's the only acceptable word to them. Don't ask me why, they can be very awkward sometimes, a lot of the time. So what does superposes mean? That means that displacements sum at every point. They add up. Let's talk about nodes and antinodes. Nodes occur when waves always destructively interfere. See, we say interfere destructively, but I don't know, maybe they want superpose. I don't care at this point. They always destructively interfere out of phase, and they sum to 0. Antinodes occur, probably say where as opposed to when, to be perfectly honest. Antinodes occur where waves constructively interfere, can be in phase. Don't forget that at an antinode, we don't always get constructive interference. The point is that we do get constructive interference at those points, so we end up with a maximum amplitude at those points. But then a quarter of a cycle or time period later, we have destructive interference. Point is that it's going up and down, and it has to go through that equilibrium between the two. So, how much detail have I put there? Quite a lot. More than is needed by the mark scheme for this particular question? Maybe, but it's always best to put more information than less, just in case AQA are expecting that level of detail in your answer. 2.2, why does the chocolate only melt at these points? Points are where antinodes occur, at an antinode, not at a node. This is where most energy is transferred to the chocolate. We can say, just to be sure, amplitude is maximum. So what's the frequency going to be? Well, what can we deduce from the diagram? We can measure the wavelength. Now the wavelength is not going to be from one point to the other. No, because if we draw what's going on with the wave, we know that there has to be an antinode here and an antinode here and an antinode here. So therefore that's what we get. So therefore this isn't one wavelength. No, it's the distance from the first to the third point. So measuring that on a piece of paper, that should give you something like 11.8 centimeters. Put that in meters, seeing that we know we're going to have to use that in an equation. Okay, so we want frequency, we have wavelength. What else do we know? We know that these are microwaves, so therefore the speed, v, or c, I prefer v, is 3 times 10 to the 8 meters per second. Because it's EM, it's a microwave. So therefore v equals f lambda. Rearranging that, frequency is equal to speed over wavelength. So that is going to be 3 times 10 to the 8 divided by that 0.118. And that gives us, well, to 2 sig figs, that gives us 2.5 times 10 to the 9 hertz. Even though our wavelength was to 3 sig figs, technically, if you look at our formula sheet, the speed of light is given to 2 sig figs. So that means we have to give our answer to 2 sig figs. So why do we want the table to turn? To ensure that as much of the chocolate or whatever food we have is heated. Otherwise we just have really hot points in our food, and actually you still do get that in your microwaved food. And we can say antinodes move relative to the food. Onto a bit of materials, a Young modulus. So what is tensile stress? Well, we know stress from our equation is force divided by area. So therefore we can say that that is force exerted or experienced per unit area. Whenever we give a definition, we don't go for actual units, we just say per unit whatever it is. Strain, we know that that is change in length divided by original length. So therefore we can say that that is the ratio of extension to original length. So what is A like on our graph? Well, we know it has a steep gradient, so therefore it's going to have a high Young modulus, and also doesn't have a plastic region. So we could go for either one of those. So we could say steep gradient, and for no plastic region, that means that it is brittle. It's just going to snap instead of stretch really that much. So we can say line does not curve at top. And we can say, therefore, it has no plastic region. So what do we have? We have a diameter of 1.5 times 10 to the minus 4 meters. If we're doing any calculations with materials, we know we're going to have to find area. So let's do that first. Don't try and do it all in one go, because if you get the answer wrong at the end, but you get the area right, then you can get 1 mark. So we know that if we're dealing with diameter, then it's pi d squared over 4. And well, we should really do it to 2 sig figs, but seeing that that's not going to be our final answer, let's be a bit more accurate, because it's only our final value that needs to be to the right number of sig figs. What else are we told? We're told the breaking stress is 1.3 gigapascals, so 1.3 times 10 to the 9 pascals. And we're being asked to find the force. So we know that stress is equal to force divided by area. So therefore, rearranging this, force is going to be stress times the area. So that's going to be, and always write down your calculation with numbers as well, because again, you can pick up on marks even if you get your final value wrong. So say you put it into your calculator wrong. And this is where we should give our answer to 2 sig figs is 23 newtons, because our diameter and stress were both given to 2 sig figs. Okay, so what do we want these materials to be like? So for the lift, it has to be quote unquote strong, and we don't want it to be brittle because we don't want it to snap, do we? In a toss-up, we'd like it to stretch a bit and not break. And then the bungee, we want it to be very stretchy, and again, not brittle. So let's have a look at our materials then. Well, B and C are, well, fairly similar. So I'm going to say that for the lift, we can choose B or C. Both have a high Young modulus. So that means that they can support the lift We can say they also have a high breaking stress. In a toss-up though, it should probably be material B. Bungee, of course, we want D. It has a low young modulus. We can say it has large strains. It's not brittle. And the fact that it goes up a little bit at the end there shows that that isn't actually a plastic region. Even though it's very long, it's not a plastic region. This shows that all the way to the end, it's not extending plastically. So we can say extends elastically, therefore will return to original shape or original length. It's a little bit mean for a 6 marker, this one, because they are looking for more things. There's more things we can say, such as what not to choose. So we wouldn't want to choose A for the lift because it will just break without warning, whereas B and C, they do go past the limit of proportionality a little bit, which means that if something's wrong, then it will be fairly obvious and you should be able to fix it before anything bad happens. And then for the bungee, of course, we're not going to choose A, B or C because they have a high young modulus, which means that the force felt by the person doing the bungee jump while they're decelerating is going to be so extreme they're probably going to break their neck or something. Okay, a bit of electricity. Resistivity. We have the resistivity of the wire, 9.7 times 10 to the minus 8 ohm meters. We have the resistance, 0.07 ohms. And we have the length of 0.5 meters. We're being asked to find out the diameter. Of course, we're going to have to find out the area in order to get to that point. So let's do that. Let's get out our equation for resistivity. R is equal to rho L over A. We're looking for area, so we can just swap round A and R. So therefore, area is going to be resistivity times length divided by the resistance. So let's write down what numbers we're going to put in. And all of our data is the 2 sig figs, even though I'm not writing them down in the calculation necessarily. And that gives us an area of, well, we don't need to go to 2 sig figs yet because, of course, this isn't our final answer. So that gives us an area of 6.929 times 10 to the minus 7 meters squared. We know the area is equal to pi d squared over 4. Therefore, rearranging this, the diameter is going to be equal to 4 lots of the area divided by pi, and then that's all square rooted. And it gives us a diameter of 9.4. We do need to go to 2 sig figs this time. 9.4 times 10 to the minus 4 meters. Okay, we have a fairly complicated circuit here. So we have our R1, R2. We have these points here, so we're probably going to have to guaranteed put a voltmeter between those at some point. We have our probe, and we have our variable resistor R3 there. And we know that the PD across all of this is 1.5 volts due to the battery being that. Okay, so the current in the cell, so the total current, we're told, so I'm going to write down I total. It's a good thing to do because then when you use Ohm's law, you're going to be sure what you're doing the calculation for. Calculate the total resistance of the circuit. So we're being asked to find out our total. And we know the total voltage is 1.5 volts. So therefore, we're going to use V equals IR. But can you see, I've made sure that I know what I'm doing it for. Total voltage equals total current times total resistance. All of electricity always comes down to just V equals IR essentially. But you have to use that for different parts of the circuit. In this case, we're using it for the whole of the circuit, and I guarantee you later on, we're going to have to keep one of those values the same. It's probably going to be the voltage, and we're going to have to use V equals IR again for just one of the components or two of the components in the branches above. So therefore, dropping the totals, it's just going to be resistance is voltage divided by current. So it's going to be 1.55 divided by 0.66. And that gives us to 2 sig figs, 2.3 ohms. Some of my students are obsessed with writing down next to their answer 2SF to make sure that I know that it's 2 sig figs. You don't need that. You just need to give your answer to the appropriate number of sig figs. What have we been asked now? So the resistance of R2 is 22 ohms. R3 is 1.2 ohms. We're being asked to find the current in R3. So we are talking about this bottom branch here. So we're thinking in terms of the 2 resistors in 1 right now. So let's go with V equals IR. What do we know? Well, we know that the resistance is going to be both of those added up. So it's going to be 23.2 ohms. What else do we know? Well, we know the voltage is the same because it's parallel, so it's 1.5 volts. Hence, therefore, current is going to be V divided by R, so that's 1.5 volts divided by the 23.2 ohms, and that gives us to 2 sig figs 0.065 amps. And again, it has to be to 2 sig figs because our voltage is to 2 sig figs. Okay, next we're being asked to find the resistance of the probe when R1 is 2.4 ohms. Okay, so now we're dealing with the top branch here. Now, what do we know about the top branch, or what can we find out about the top branch? Well, first of all, we know that voltage, again, is 1.5 volts. And also, we can find out the current in the top branch as well. Why? Because we know that going into here, there was 0.66 amps. That was our total current. But then going down here, we have a current of 0.065 amps. So therefore, going up here, we must have one take away the other. So 0.66 take away 0.065, and that gives us a current in the top branch of 0.595 amps. Cool, so we know the voltage in the top branch, we know the current in the top branch, so now we can find out the resistance in the top branch, the total resistance of R1 and the probe. So it's easy to get caught up with the fact that we've been given the resistance of R1. You might want to use that straight away, but just hold your horses. Just first of all, look at what you have and what you can find out first. So V equals IR, therefore R is going to be V over I. So that's our 1.5 volts divided by 0.595, and that gives us 2.52 ohms. So the total resistance of the top branch there is that 2.52 ohms. So what I can say is R1 plus RP, resistance of the probe, is that 2.52 ohms. Therefore, the resistance of the probe is going to be that 2.52. Take away the resistance of R1, and so that leaves us with 0.12 ohms. Not the easiest electricity question in the world, lots of different things going on. You just need to keep your head on straight and write down what you have, what you've been given, and use V equals IR, but thinking clearly, what is that for? Is it for the whole circuit? Is it for a branch? Or is it for an individual component? There are other ways that you could have done a couple of these steps, but that's the way that I would have done it. 4.5, what's the percentage change in the diameter when the resistance increases by 1.6%? Okay, so let's crack out our equation again for resistivity. This is a proportionality question because we're being asked to find out how a relative change in one thing affects a relative change in another. So resistance is rho L over A, but we're not concerned with how resistance is affected by area. Therefore, we can say that resistance is inversely proportional to the area because we're saying that resistivity and length are constant. Okay, but here's the thing. We're actually not looking for resistance. We're looking for diameter, how it affects diameter. We know that area is equal to pi d squared over 4. So that means that area is proportional to d squared. We don't care about the constants there. So that means I can actually replace area in my proportionality equation with d squared. So therefore I can say that swapping these two around, d squared is proportional to 1 over the resistance. But we're not concerned with how diameter squared is affected, but rather diameter itself. So we're going to square root the whole thing. So diameter is going to be inversely proportional to the square root of the resistance. Now, I actually really disagree with the mark scheme here. They've been very, very lazy. They say, hey, you know, if resistance has to go up by 1.6, then that means diameter goes down by 0.8%. Things don't really work like that, actually. So let's do this properly, shall we? We know that R has gone up by 1.6%. So therefore, we can say that this R has gone up to 1.016 times its original value. So then plugging the numbers in, we end up with a value of 0.992, and it goes on from there. So that means that this has gone to 99.2% of its original value, so therefore it's gone down by 0.8%. However, the mark scheme implies that it's gone down exactly 0.8%, but that's not the way that maths works, and we've just proven that, and we've done it the right way. So we have a voltmeter connected to A and B. And we're told that the voltage is going to be constant, even if the battery is changed to one that has an internal resistance. What does that mean if something has an internal resistance? That means that some of the total EMF or total voltage is being lost inside the battery before it gets to the circuit. So that means there's less of that voltage available for the circuit. We can say, to be proper, that there's a lower terminal PED. So this is not an easy question. But basically all we have to say is that, well, the resistances haven't changed. So that means that the voltage between those two branches at those points is going to stay constant. That's a really mean question. I think that they should have asked you to find that out mathematically, because then it makes a lot more sense. Asking you to explain that when it's something that we don't usually talk about is really mean. I give this question an F. Okay, photoelectric effect questions. We always have to answer them in terms of energy. Energy of photons, energy of electrons. Sometimes people forget to do that. So let's try and do this properly. First thing we say is that the energy of a photon is equal to hf. So therefore we can say that energy is proportional to frequency. We can say that the energy required, or rather the minimum energy required to liberate an electron from the surface of a metal, is what we call the work function. We give that the symbol phi, and that's equal to hf0, where f0 is the threshold frequency. Current only flows when the energy of a photon, E gamma I can say, is greater than hf0, so that electrons escape the surface to the wire electrode, and current flows. 5.2, what happens to the current when the intensity of the source increases? Now, this is a little bit mean. I don't like it when they ask this, because they assume that you're going to assume that the frequency of the light source or EM source is staying constant. They don't really say that. I think they should have to say that. So what they're really saying is what happens when we just increase the number of photons being emitted per second by the source. So an increased intensity is achieved by increasing the number of photons emitted per second. That is, if the frequency is constant, the energy of the photons is constant. This results in more electrons liberated per second, and so therefore the current increases. Enough of the wordy questions. Let's do some maths. Okay, here we go. 5.3. We have the work function of 2.1 electron volts. We might have to turn that into joules in a minute. Don't know quite yet. We'll cross that bridge when we come to it. We have the frequency of 7.23 times 10 to the 14 hertz. And we're being asked to find out the maximum kinetic energy. So our equation is EK max is equal to HF minus phi. We have H, we have F, and we have phi as well. But we are going to have to turn it into joules after all. So I'm going to do this all in one go. So H times F, that's 6.63 times 10 to the minus 34 times 7.23 times 10 to the 14. Let's sort out powers of 10, minus 34. Plus 14, so that leaves us with minus 20. Then we're going to take away the work function, so there's 2.1 electron volts, but then we have to multiply that by 1.6 times 10 to the minus 19. That's what each electron volt is worth in joules. And that gives us the two sig figs, 1.4 times 10 to the minus 19 joules. I was probably a bit naughty doing that phi in one go. Probably should have calculated it first, just to make sure that I can get that mark. If I do that, 2.1 times 1.6 times 10 to the minus 19, I end up with 3.36 times 10 to the minus 19 joules. That's the work function. Okay, 5.4, we're being asked to find out the stopping potential. People struggle a lot with this, but we just need to remember, first of all, what voltage actually is, or what PD is. Voltage is joules per coulomb, so the energy per coulomb of charge. So the equation is V equals E over Q, energy over charge. If we're talking about this specific situation, we're talking the stopping potential, so Vs is equal to the EK max, but I'll just call it EK, divided by the charge of one electron. So all we have to do is plug those numbers in. 1.4 times 10 to the minus 19, that's our max kinetic energy, divided by 1.6 times 10 to the minus 19, so it's just 1.4 divided by 1.6, and that gives us 0.89 volts. 5.5, we're being asked what happens to the stopping potential if the frequency is increased. Nice and easy, but again, we have to talk about it in terms of energy. So, because E is equal to HF, that means that each photon has a higher energy. We can just call it E gamma like earlier. Therefore, that means that EK max is increased because each electron gets more energy. So therefore, the stopping potential is increased. A higher potential is needed to stop those electrons from crossing the gap. 6.1, we're looking at some particle physics or nuclear here. We have the rest energy of a helium nucleus is 3,728 mega electron volts. We know that that's rest energy, so that's equal to mc squared. First things first, we're being asked what is meant by isotopes. Isotopes are nuclei with the same atomic number, that's the same number of protons, but different numbers of neutrons. Nice and easy. 6.2, why is it that we have 2 photons produced by annihilation as opposed to 1? That's in order for total momentum to be conserved, and the photons have equal and opposite momentums or momenta, so that is achieved. 6.3, we're being asked to find the frequency of said photons, or rather the minimum frequency. Minimum frequency means if we assume that there's no kinetic energy going in with the 2 annihilating particles, so we just have our rest energy going in. So let's find out what the rest energy is. So we take our 3,728 mega electron volts times by 1.6 times 10 to the minus 13, because it's mega electron volts. That gives us 1.193 times 10 to the minus 9 joules. Okay, when it comes to annihilation and pair production, I always like to draw a diagram. Here's my 2 particles going in, and then my 2 photons coming out. We know the energy of those particles going in equals the energy of those photons coming out. So actually, I can just divide the whole thing in half. I can say the energy of 1 helium nucleus going in is equal to the energy of 1 photon coming out. So I can say that the rest energy is equal to the energy of the photon. So therefore, that's equal to HF. Rearranging that, frequency is equal to the energy, rest energy, just left it as E though, divided by Planck's constant. And that gives us 4 sig figs, 8.997 times 10 to the 23. Now our data has been given a 4 sig figs, but we have used in there 1.6, or rather 1.60 times 10 to the minus 13 from our formula sheet. So if we're doing it to 3 sig figs, then we're just going to round it to 9.00 times 10 to the 23 hertz. 6.4, complete this interaction. So we have this anti-neutron going in, makes this anti-proton, and 2 more particles. We know that when we have a neutron turning into a proton or anything like that, we are going to have a neutrino of some sort made. So I'm going to pop that on the end. I don't know exactly what it's going to be yet, but we know it has a mass and a charge of 0. What's the other particle going to be? Well, let's just look at the masses. We have 1 going in, 1 coming out, so therefore it has to have a mass of effectively 0. Think about the charges, 0 going in, minus 1 coming out, therefore we must have a plus 1 coming out as well. Therefore, it's going to be a positron. So we can either put beta plus, or an E plus, or an E hat. I would go with E plus personally. Let's just check the neutrino. This is all to do with lepton number. So no lepton going in. And we know that an electron is the daddy of leptons, as it were, so it has a lepton number of plus 1, so therefore a positron has a lepton number of minus 1, so therefore it has to be a neutrino as opposed to an antineutrino. And we might want to put a little subscript E for electron neutrino after the neutrino symbol. 6.5, nice and easy one to finish off with. What interaction is responsible? Well, there are leptons involved, so therefore it must be the weak interaction or weak nuclear interaction. So I hope you found that helpful. If you did, please leave a like. If you want to go on to paper 2, then click on the card and it'll take you there. See you next time.